Okay, these are the notes for section 5.5. We're going to do multi-angle and product of sum formulas. Basically, we're going to focus on double angles and half angle formulas. So the first set is the double angle formulas. As you can see, if you look closely, the double angle formulas are actually derived from the sum and difference formulas. So if we take, so I'll focus on just sine. So if you take sine, you've got this double u, so 2u. And break it down into u plus u, which we know. Now you can use the sine, cosine, cosine, sine. But then when you combine like terms, because the u's are the same thing, so the angles are the same, you get the double angle formula for sine. So it's totally based off of the sum and difference formulas. You can see the exact same thing with cosine. Now cosine, because it actually results in cosine squared minus sine squared, there's actually a couple derivations of it. So what you can do is you can use cosine squared minus sine squared, which I'm a big fan of. That's kind of the one that I lean towards. And I'll explain as we go why. Then you can even replace like the cosine squared with 1 minus sine squared using the Pythagorean identity. So another version of the formula is 1 minus 2 sine squared. Or you can go back to cosine squared minus sine squared and replace the sine squared with 1 minus cosine squared, which gives you the third version of the double angle formula for cosine. It doesn't matter which one you use. My recommendation is find the one that you like the best and kind of lean towards that one. If you want to, I know one thing that people do is based off of what's given, that's the version that they use. So let's say that you're given sine of u. Okay, so then they're going to gravitate towards the 1 minus 2 sine squared u because they've already got sine u. So I get that. But personally, I would just recommend find the one that makes the most sense to you and put that one in your memory banks. You can see the exact same thing here with tangent. And then just a quick reminder, tangent is always sine over cosine. So as long as the angles match, you're fine. You can use that as well. Okay, so we have our first example. We're going to find the exact value. So again, we're not going to give decimals on this. And we have that sine is 7 over 25, which is acceptable for sine. And then it's between negative pi over 2 and pi over 2. So my recommendation is draw a picture, and then we can start working with it. So put it in the correct location, and then go ahead and find the missing side using the Pythagorean theorem. So I know this is going to be 24. And then just check positive, positive, positive since you're in quadrant 1. Okay, let's just jump into the formulas. So we know that sine 2u only has one version of its formula, and that's 2 sine u cosine u. So just grab the values. So this is 2 times, well, the sine in the picture is 7 over 25 times cosine in the picture is 24 over 25. Just put a 1 underneath your 2 and multiply straight across. This is going to give us 336 over 625. Okay, so that's sine 2u. So let's do cosine 2u. Now remember, this one has a couple versions, so pick the one that you like. Now, I tend to gravitate towards cosine squared minus sine squared, and I'll show you why. If I put my cosine in and my sine in, you'll notice, and this is kind of the thing that seals the deal for me, is that the denominators of these already match. So when I square these, the denominators are going to match. So then I can just subtract the numerators. Like I don't have to go through the process of getting a common denominator. That's really kind of it. Whereas if you did one of the other versions, so 1 minus 2 sine squared u, you would have that 1 where you'd have to get a common denominator and then you'd subtract. I'm not saying it's difficult or impossible to do, but as far as I'm concerned, it's one extra thing I would have to do. So I'm a big fan of using cosine squared minus sine squared. It's really the one that I lean pretty heavily on. So if I type that in, if I do the math, I get 527 over 625. Okay, tangent to u. If I have to go through the process of finding sine 2u and cosine 2u, when I find tangent 2u, I'm going to use the other two answers. So go back, do a quick check, make sure that you're confident on your answers for sine and cosine, because if they're wrong, then tangent's wrong. Or if one of them is wrong. You can also just use the formula for the double angle for tangent. I feel pretty good about my work for sine 2u and cosine 2u, so I'm going to use those. Now, just as a reminder, if you have the denominators the same, so we'll go off to the side for a moment. I'm going to take this guy off to the side, and I'm going to take that guy off to the side. If I do 336 over 625, which was sine, over cosine, 527 over 625. Remember, this is a division problem. When you divide by a fraction, you technically multiply by the reciprocal. We've done this for a while. If the denominators of both of these fractions are the same, they cancel with that multiplication happening. So actually, I just get 336 over 527. So I'll just bring this guy over here. Another reason why I like the cosine squared minus sine squared, because then it guarantees that I have the same denominator too. Although the other way will as well. Okay. We'll take a look at the next one. Okay, so why don't you pause the video, see if you can draw the picture in the correct location, and see if you can identify the missing side, then come back and check yours against mine. Okay, so we should be in quadrant 2. Basically between pi over 2 and pi, because that's where cosine is going to be negative if you're between 0 and pi. I went through and I put the -7 on the adjacent side, 9 on the hypotenuse, and then I did the Pythagorean theorem to find out that the height was actually the square root of 32. Okay, now, here's my recommendation. There's only 3 formulas. Well, there's multiple of cosine, but there's not a ton. What I want you to do is I want you to see if you can go through and do all of sine 2u, all of cosine 2u, and all of tangent 2u. Then come back and check your answers here. Okay, so there's only one double angle formula for sine, so it's 2 sine u cosine u. So I've got 2 times my sine of the u triangle, square root of 32 over 9, and then the cosine of that triangle is -7 over 9. If I go through and I multiply these straight across, let's put a 1 underneath that 2. This is going to give me 2 times -7 is -14. Just kind of carry the root 32 with you. And then 9 times 9 gives us 81. So that's our sine 2u. Okay, now if you haven't tried cosine 2u, pause the video, see if you can do it, come back and check. Okay, so I'm still gravitating towards that single formula for cosine of the double angle, which is cosine squared minus sine squared. Again, you can use the other ones. You're more than welcome to. They work. So if you go through, plug the stuff in that you need. This is going to end up giving me 49 over 81 here. And then just as a reminder, when you have a square and a square root, so like if you distribute it here, those guys are going to cancel. This is just going to give me 32. Don't forget to square the bottom. That's 81. So then if I subtract these, then I'm going to get 17 over 81. Okay, now, if you're confident with your sine and your cosine, which I am going to go through and do my tangent. Now, if you want to pause at this moment, see if you can get tangent 2u, go right ahead. I'm just going to go ahead and keep going through with this. So I know that sine over cosine is the exact same thing as tangent. I already did this. And I noticed that the denominators on both of those are going to be the same, so that when I pull them together, they're going to cancel. So I'm going to have -14 root 32 over 17. So remember, the first part, this comes from the sine 2u. And this bottom part comes from cosine 2u. Now, I'm not going to say exactly sine 2u and cosine 2u because the denominator is canceled. So those aren't the exact values. When I pulled them together, though, the 81s went away. Okay, now solve. All right, so we want to be able to use these double angle formulas to actually be able to solve an equation. Well, previously, when we solved equations, we had the case where the angles all matched. So all of them were theta, or all of them were x, or all of them were for x and we called it theta or u or whatever. We have an issue here though. This problem is these angles do not match. We need them to match. So they either need to both be double angles, and then we can do u substitution like we did a couple of videos ago, or they both need to be single angles. So they both need to be x. So I have to match the angles no matter what. So if I take a look, I can actually turn this guy into a single x using the double angle formula. So let's use the double angle formula here. Because then we'll have just a single x and it'll match that angle right there. So I've got my 2 cosine x plus, and then I'm going to replace the sine 2x with 2 sine x cosine x. So use the double angle formula. 0. Now the angles match. They're all x's. They're all the same angle. And now we can proceed. Okay, well, if you look, they have a 2 in common and a cosine x. So let's factor. So this is going to be 1 plus sine x is equal to 0, zero product property. So the only thing that was different to start this was that we had to get the angles to match. And then I'm going to do the same thing that I did before. So let's put this on the unit circle. So cosine is equal to 0 here and here. And that has a consistent distance. Okay, let's check this guy over here. Sine is equal to -1 here. Oh, okay, so these repeat over here. Now I don't need to be repetitive about this. I don't have to state multiple times that 3 pi over 2 is an answer. So I can actually wrap this all into one thing because I have this consistent distance between all of the answers of plus or minus pi. Okay, so we have x equals pi over 2 plus or minus pi n. And that takes care of all of the answers. Okay. Okay, now verify. Okay, so we've got the same situation here. So you want to use the double angle formula. I think I'm actually going to do the left-hand side. It doesn't look like it has more stuff, but it kind of does because I have a double angle that I can break down into one single angle using the formula. So I am going to stick with that guy. I know how to take a double angle and break it down into pieces. I'm not totally sure how I'm supposed to take single angles on the right-hand side and turn those into doubles. So I would have to be able to do like reverse of the formula. All right, which I can do. Like it's possible. Both sides are totally fine. So if I do, of 2 theta is actually 1 over sine 2 theta. And then remember this is a proof. So carry everything down. So cosecant theta over 2 cosine theta. Okay, now let's use the double angle formula. So this is 2 sine theta cosine theta equals cosecant theta 2 cosine theta. Okay, I'm almost there. So I'm going to go ahead and pull this apart. So I want to pull the sine theta off of the 2 cosine theta. Now, I see the 2 cosine theta on the bottom. Let's take this first guy and flip him over. That's actually cosecant theta. And now let's push them back together. Again, this isn't the only way to do this. You could have worked the right-hand side. And actually, it might be the same amount of steps, or it might actually be less. But it's whatever you're comfortable with or can recognize when you're doing your proof problems. Okay, so there's our proof. Okay, so now we've got the half-angle formulas. The derivation of the half-angle formulas also comes from the sum and difference formulas. It does. So it's the fact that if you wanted to, so the basic of this, I'm not going to get into this too much. If you wanted to do sine of theta, we know that this is sine of theta over 2 plus theta over 2. Then you could do the sum and difference. Then you'll end up breaking it down into a sine squared. And then you'll end up square rooting it to get back to, so to just get the sine theta over 2. So you can actually start with sum and difference, do a little bit of derivation, and get to these half angle formulas. Okay, taking a look at the half angle formulas. One of the things, they're very similar to each other, sine and cosine, so just be careful. And then you have this plus minus in front. That's because we square rooted at some point. So the plus minus is dependent on the quadrant where that angle is located. So we're going to have to do a tiny bit more legwork. And then we know that tangent is the exact same thing as sine over cosine. And then there's actually a couple other variations of this that you might appreciate using. So let's say you don't have to do sine of theta over 2 and cosine of theta over 2. Maybe you just need to go straight to tangent of theta over 2. Well, then these guys might be an option for you, those two variations. So you have a couple to choose from. Okay, let's take a look at this guy on the bottom. Okay, calculate the exact values. Okay, given, okay, so why don't you pause? We're doing a ton of pictures. So why don't you pause, see if you can draw the picture and put this in the correct location. Okay, so we should be down in quadrant 4. So if you're between pi and 2 pi for theta, and you need your cosine value to be positive, well, that's have to be to the right from the origin. It can't be left. Okay, so this is where theta is located. Let's go through and figure out where theta over 2 would be located. So if I take a look at this location itself, it looks like theta is somewhere in quadrant 4. So in quadrant 4. Well, quadrant 4 technically between 3 pi over 2 and 2 pi. So we basically took the pi to 2 pi and we actually shrunk it a little bit more. I want to find where theta over 2 is located. So here's what I'm going to do. I am going to divide theta by 2. But then I have to divide everybody by 2. So I'm going to shrink all of them to a theta over 2. Okay, so this is going to give me a 3 pi over 4. This is going to give me a theta over 2, which is what I'm looking for, and that's going to give me pi. Okay, so let's think about where this is located. I want to be at 3 pi over 4. So 3 pi over 4 and pi. So that means somewhere in here is where theta over 2 is. Somewhere in there. I don't know where exactly. I just know it's in there. So if I take a look at that, between 3 pi over 4 and pi, I know that that means that sine of theta over 2 has to be positive because it's up. And I know that cosine of theta over 2 has to be negative because it is left. So I'm going to grab these guys and pull them up so that we have them. So I need to keep that in mind when I go through and do sine of theta over 2 and cosine of theta over 2. Okay, so now let's grab our formulas. So I've got sine of theta over 2 is equal to positive square root 1 minus, okay, the cosine value of theta itself. Well, the cosine value from my theta triangle is 5 over 13 divided by 2. That's positive. So this is actually going to give me 8 over 13 divided by 2, which is, and I don't need to keep the positive, like it's understood that it's there. This is 4 over 13. Now if I square root them separately, this is 2 over the square root of 13. Okay, let's take a look at cosine. So cosine of theta over 2, we decided was negative square root 1 plus 5 over 13 all over 2. Do the math. It's negative. This is going to be 18 over 13 over 2. Got to keep the negative sign. This is 9 over 13, negative 3 over the square root of 13. And then tangent of theta over 2. I'm just going to use my sine and my cosine. Take a look. The denominators are the same, so when I pull it together, they're going to disappear. This is just going to give me negative 2/3. And that brings us to the end.